The moon is about 384,000 kilometers away.
And the sun is 150 million kilometers away.
The nearest star is over 40 trillion kilometers away.
But how do we know this? How can we measure things we can't reach, can't touch, can't even walk to? What if I told you it all begins with this? Let me show you something. I'm standing in front of Purdue's Engineering Foundry. Let's look at the bell tower and observe what happens when I take just a few steps to my right. The bell tower moved. According to space.com, this is the definition of parallax. Parallax is the apparent shift of an object's position when seen from two different positions. This happens because your line of sight changes, and from this shift, we can calculate the object's distance. Let's break this down.
Okay, so I had to destroy my kitchen for this, so hopefully this makes some sense. Suppose I had this set up here, right? That Coke can is a celestial body that I wanted to measure the distance to. And these are you. And imagine that we're stuck in this part of the table. How do we measure the distance? Okay, to do this, we first have observer 1 here. Then we have observer 2 here, that are some known distance apart. So let's say 50 centimeters in this case. From the perspective of observer 1, the can is right there, roughly aligned with my light's stand. From the perspective of the second guy, the can looks significantly shifted from the light stand. So the goal of measuring distances with parallax is to find this angle theta. Since you have two observations from two different places, you can calculate the amount the object of interest has shifted. And with this, if you know your camera's field of view, you can convert this into degrees. And it turns out that that angle is actually this angle theta. And since you know theta, and you know the distances between the two observers, you can calculate the distance with this formula. All you have to do is plug in the values and calculate your distance.
We can use the same method to measure the distance to the moon. Two observers on opposite ends of the Earth can notice a slight offset in the moon's position in the sky. Measure that offset and use our baseline, which is the diameter of the Earth, and plug that into our formula. The sun works the same way, but the parallax angle is tiny, so we need extremely precise instruments.
For stars, even the Earth's diameter isn't enough. So we use the Earth's orbit as the baseline. 300 million kilometers wide. We'll take a photo of stars in January, then another in July. And if the star appears to shift in the distant background, that's stellar parallax. A star that shifts by 1 arcsecond, that's 1/3600th of a degree, is 1 parsec away. That's about 3.26 light years. But most stars and galaxies are too far away. Parallax won't work. The angle is too small to measure. So we use something else, redshift. According to a page NASA.org created in 2024, redshift in Hubble's law describes that as light is emitted by stars and galaxies, the light is stretched the farther away they get, creating from a blue color to a red color. We use this to measure the distance.
All of this, triangulation, redshift, parsecs, all of this started simply from just noticing that things shift when we move.
In just 500 years, we went from guessing to measuring trillions of kilometers. But why does this matter?
Why does anything matter? Because it means we can understand from this tiny planet, we can map the cosmos.
And if we've gone this far already, just imagine how far we'll go.